Okay, hello again. What we were talking about? We were talking about global variables, if you remember. So you see a piece of code here. Well, that was a quick start, guys. Sorry, but we start anyway. So this is a piece of code. If you remember, we've talked about this and we called it the global variable. Why? Well, this piece of code is not an assembly instruction. It is the directives that comes before the code. You remember, if you just check a simple project, or this is one of the old lab projects, and these are the directives, and this is the code instructions. And this piece is actually part of a directive. And you're not responsible for directives, but understanding what directives are will help you understand your code and instructions. So actually, this guy is allocating a piece of memory in the data memory of 40 cells, each cell being 1 byte, so 40 bytes. And I'm asking the compiler to make an assignment. Assign the name M to the start of this piece of memory. So this is a 40 byte piece of memory. It means there are 40 addresses because there are 40 cells. The first address, starting address, they are, adjacent, they are sequential. It starts from M to M plus 39 because total 40. This starting address, I will assign it as M. I don't have to know where it is. Just you decide where it is, compiler. I'm going to be using it in my codes. How? We have seen it, and we are going to continue this stuff. Actually, this week, this is week 8 stuff, but I explained this to you in the previous week. Maybe you'll remember that in the previous year's syllabus, there were different midterm weeks and there were some vacations. So to catch up with this year's academic calendar, we are making some shifts. So this was a 1 lecture week then, a couple of years ago. So we are going to finish it this week and we're going to continue by week 9, starting with next week. So week 9 of the previous weeks will be week 8 of this year. I hope you understand. It was a bit complicated. So we continue with characters, ASCII, and strings. So guys, characters and ASCII. You don't know, maybe some of you may recognize ASCII, what is ASCII, but I'm going to explain it. But you know, characters are and strings are. Actually, this is a string. If you can read something on the screen, then that must be a string. Well, up to now, we've been talking about computers, microprocessors, and all we said was there are registers inside microprocessors, there are data memory or instruction memory, and everything is represented by binary values inside the computer. I guess you got it. It's so simple. However, we can understand the computer. There is text. There are other. So how does the computer keep them? So there must be a way. Is the architecture of the microprocessor inside this desktop I'm using right now, is it different so that it can keep characters? No. All microprocessors have the same architecture, more or less. And the thing in common is they only use binary values. So inside the registers or the memory of any computer, guys, your washing machine, your phone, your desktop, everything is binary. So how do I understand things like text or graphics? The basic answer is somehow they should be encoded. Encoding means there's a code for each of them. So it is like a table. And actually that table's name is ASCII. That's what we are going to learn today. So characters. Everything represented by a computer is represented by binary sequences. Just what we said. A common non-integer to be represented is a character. In computers, there are many non-integer things that you want to represent, like a pixel on the screen. But one of them, and the most common of them, and the most basic, fundamental of them, is a character. For this, we use a standard encoding to represent characters, which means each character will be mapped to a binary value on a table. And everybody will agree on that table. So some guy writing some text on a computer in China will use the same table so that I will be able to read it when I see a part of that memory, for example. Or if that binary sequence reaches me, I will be able to decode it. in some ways because it was encoded using the same table. What is that table? It is called a standard code, American Standard for Computer Information Interchange, ASCII, because it was the Americans who first found it, but the entire planet is using it right now. It defines what the characters are represented by each sequence. So that table is called ASCII. And if you look up the ASCII table, you'll see the binary sequences for each character. Let's do it. So guys, what is ASCII table? Before seeing the table, we have got some sentences. Let's go over them. There are codes in the table and they are called the ASCII codes. This is, pronounced as ASCII, as if you're reading it, the abbreviation. It represents text in computers, telecommunications equipment, and other devices. So it is not only computers, guys. For example, your computers and your phones are connected to each other via the internet, right? And you're sending packets in the internet. And some of you will get some courses on computer networks, for example, if you have taken it already, but it's a elective course by Barbaros. Barbaros is, very competent on computer-related stuff because he's a computer engineering originally. So in his lesson, you will learn that all networks will communicate using so-called internet packets. And in those packets, there's a place you keep the data. And you're texting with your friend. How does the information go? Well, you're saying hi, for example. You have to send H and I as characters. Those H and I are represented as binary sequences. And there goes, and the other phone just can decode it because they are using the same table, which is the ASCII table. Everybody uses the ASCII table. Okay. Most modern character encoding schemes are based on ASCII. ASCII is a bit limited because it has got only 256 elements, but in today's characters, we need more. there is Chinese characters, which is like 5,000. And there are Turkish, some Turkish letters like she, che. Che is represented in ASCII, but she, yumuşak G is not. And ASCII had to be extended. But all the encoding schemes for characters are based on ASCII. And the basic set ASCII is universally accepted, guys. This is what we're going to be seeing, okay? Basic ASCII, that fundamental set everybody agrees on, is in 8 bits, which means every character is represented by 8 bits. So for example, what I'm trying to say is, there is a character, for example, A. It is represented by an 8-bit sequence. This is not the real sequence, but I'm just imagining so. So 8 binary numbers. Okay. As you can see, since in ASCII, every character is represented with 8-bit numbers, there are a total number of elements you can represent. You can either write 0, 0, 0, and 0, 0, 0, 0 in binary, the smallest number, which is in decimal 0, and 1, 1, 1, 1, and 1, 1, 1, 1 in binary, which is 255. So a total of 256 elements in ASCII because it's 8 bits, guys. That's why ASCII table is 256 elements long. Let's see the table. Let's see the table. That's the table. You're just looking at the table. You don't have to memorize it. It's just the table and you'll need it. If you have to just look at it, you can always look at it just like a reference table. But it's there, and actually it's there. And I've just annotated some of the ones. So as you can see, this is hex. So E is by hex 45, D is 44, M is 44D, R is 52 hexadecimal, or anything, other characters as well. There are other characters, as you can see, we don't have much Turkish characters here, like yumuşak G or she, because they are not represented in ASCII, guys. Okay, good. So, any questions about the ASCII table and how characters are represented, guys? Any questions? I guess not. Simple, right? Okay, let me continue then. Well, so how to represent sentences or letters? How to represent a sentence? You create arrays of characters. Well, lucky for you, you've just learned arrays the previous week. And you know how to create different precision arrays, which means the size of each element in the array can be defined by you guys. You can create an 8-bit element array, 8-bit precision array, in which each element will be 8 bits. Or you can create 4 bytes, 32-bit element precision array, in which all elements individually are 32 bits. You decide how to do it. And you now know the instructions that can handle them in your assembly language, right? So guys, what we just said was, in the ASCII table, every character is represented by 8-bit values, just like this is an hexadecimal, 2 nibble hexadecimal. 2 nibbles is 8 bits, so total 8 bits. So if I create an 8-bit array in the memory, and if I say that I will represent some characters in them, actually I'm keeping an array in the memory. And if you remember, imagine if I say that these represent some characters, actually what was this? Does anybody remember in the list? This was E, guys. And this was R. Since I am a megalomaniac, I've written my own name on the slides, guys. And what was 03? Let's check. What was 03? End of text. Because when you're sending something, you just don't know how to say, I'm finished talking. Because in real life, we have a procedure for it. We are so clever that when we're talking to each other, we understand when somebody finishes their sentences. Or sometimes we don't understand, we interrupt them. Or we ask, are you finished? I was going to say something, kind of. In order to communicate in communications and computer networking, they had to create some abstract characters like that. So this is not a character. It's like an indication. But it's kept in the character list as well, because we need to represent it using binary codes as well. So in the list, this also has a meaning. And of text. So if I create such an array in the memory, and imagine another microprocessor is sharing the memory. I'm talking about an advanced concept which is beyond the scope of this course, but this might make things clear for you. So imagine this is a memory which can be simultaneously reached, accessed by 2 separate microprocessors. That's called shared memory, guys. That's an architectural design in computer engineering, advanced computer engineering today. So for example, one of the microprocessors put a message here. If the other one knew where to look, and if checked here, it could find a sentence or a word here, because I tell the guy that it starts from this memory location. I mean, this should have been, there is another 0 here. I missed. It's 20 million. Check there. It will check it. Convert the characters according to the ASCII table, and we'll be able to read them. So this will be a simple 8-bit array, because each character in the table is 8 bits. The length of a character array can be designated by a termination code. This is called the indication, is the termination code. So that although I don't know when is the shared memory, shared microprocessor, the other microprocessor reading that place, I don't know how long the sentence is or the word is, I'm sorry. I just read each text, and when I come across this one, because I read this one, this one, this one, this one, I come across this one, okay, it's finished. I can just read now, which is ASCII end of text. Okay, so that was theoretically how we keep characters in the memory, and actually that's how it exactly happens in your computers, on your phones, everything, guys. Any questions up to now? Simple, right? Okay, I'm going to do that test. Can anybody hear me?
Evet hocam.
Thanks. Okay.
Evet hocam.
Okay, so guys, how to write that? Simple. Imagine we had that. You remember the slide I've shown you first? That was the reason I wanted to show that slide from the previous week, because we have created a global variable m, and we asked the compiler to allocate a place for us. Okay, it allocated the place for us. It starts with m. I don't know what m is until I run this code. M will be automatically loaded to R2. Actually, this code is already run. You don't see the yellow triangle. It's somewhere down. So these lines of codes are already run, which means I can check the value of M at register 2. It's 20 million. So I check the positions at 20 million. And these are each cells 20 million, 20 million 1, 20 million 2. I'm talking about the memory address locations, right? Simple. So I've put this value and I've written this value to R2. There is something not quite correct with this code, guys. Can anybody correct me? Look at this instruction. Any ideas? Any ideas? No? Guys, I'm writing only a single byte, but sorry? Couldn't hear you. Maybe there's an answer. I'm writing only a single byte, but I'm using the instruction str. So does it sound correct to you? Or what else could it be? Any ideas? Yes, I can hear you.
LDR mı olması lazım hocam?
LDR reads from the memory to the registers. STR writes to the memory. That's correct. So I want to write these to the memory.
Hocam 000 olayı olacak, onu mu diyorsunuz?
Shift mi edeceğiz hocam?
Well, these are questions related to the answer, but let's not confuse you. Let's answer the question first. Let me answer your questions later. So guys, I'm trying to write a single byte to the memory, but I'm using str. Is there something wrong with this?
Hocam işte STR mı yazacağız, onu mu?
B değil mi hocam?
B or H and why?
B'di galiba.
B, because
B
this
hocam.
is 8 bits. Only 8 bits, one character. But str is 32 bits, guys. So you should have used the 32-bit version of str. This 8-bit version of str, and this should have been strb. But still, it was str, and believe me, the code worked. How did it work? Let's try to go over this code. We will understand how did it happen. So we will be dealing with arrays again. We will just stop discussing strings for a moment and go over this code. And using strb and str didn't matter much. Why? Let's see. Imagine I'm at this line. Okay, so I'm going to be drawing so I'm here, guys. I'm going to put the value of r here. So then I'm going to be writing this value using str. What is it going to write? In R0, I have this value at this point. In R0, I have this value. R0 is always 32 bits. Right? So if I use str, it's going to be copying everything because it's 32-bit instruction. So it's going to write 45 and 0, 0, 0, 0, 0, 0, 0, right? Any questions? This str. I'm doing this operation now. Any questions? Okay. Then I put R52 to R0, and I'm trying to write it to R2 plus 1 cells. So I start writing from here. And in that case, here R0 is 0000 52. It's going to write 52 0 0 0. So that's why it didn't make a difference. But in the end, I had these zeros. I had to write these zeros. If I have used strb, these wouldn't be zeros. They would be the random values which the memory had before I started my instructions. Did everybody get this detail? Okay. So still, using str, we can write these. As you can see, they are written. So it's in hexadecimals. This is in the list E, R, D, E, M, and end of text. So when we use characters, actually, we use this as well. to make them, to indicate them that they are characters. Okay, simple. So with this line of code, I could write something in the memory. If there was a mechanism like get this part of the memory and send it to the serial communication line, somebody will read it. Well, you would have been in hardware designing a chat program. Actually, we are going to do this in the next semester's course. Actually, we are going to just talk about this in this course, but next semester we have embedded systems. We will do those, how to create serial communication interfaces and use ASCIIs and arrays and stuff. Okay, simple. Okay, so by the way, as you can see the ASCII table, these were the characters, but there's something very nice about Kale. You can represent, so each 8 bits, this is a single cell, right? Cell address 20 million, cell address 20 million 1, cell address 20 million 2. Each address is 8 bits. So if each address is 8-bit, and if I'm representing ASCII characters here, I could ask Kale, hey, Kale, do not show me these hexadecimal values. Show the corresponding ASCII values. That would help me. If you say that, actually how you do it, you right-click on this screen. When you right-click, this comes, select ASCII. You're going to see it, and we are going to do this. In this case, all values will be represented by ASCII codes. And in that case, you will see that these values are 45, blah, blah, blah, blah, is ARM as well. So actually in Kale, when you're watching the memory, this is memory watch, remember? If you use ASCIIs, you can immediately see if a part of the memory is encoded by ASCII characters because you will come across some meaningful text. Any questions?
Hocam ben sormak istiyordum ama şimdi LDR'ye biz EMATA dedik ya 2'ye. Bu mi memory'e 45.00032 bitlik mi yazacak Emi?
Okay, so regarding your question, LDR reads from the memory to the registers, SDR registers to the memory. Clear?
Tamam hocam.
Okay, because you said LDR. And if you said SDR from the registers to the memory. And yes, SDR is 32 bits, SDRH is 16 bits, SDRB is 8 bits. Answer to your question?
Evet hocam.
Okay, these things get confused, I know. They are very fundamental and simple, but it takes a bit of your time not to confuse them and do them, I mean, naturally. I mean, it takes time before it becomes natural for you guys. Okay, any other questions?
Hocam benim dikkatimi çeken az önce mesela burada Erdem'i şimdi düzgün bir şekilde yazdı ya.
Hı-hı.
Ama bir de ikilik ayırıyordu. Mesela bununla öbürünün arasındaki fark nedir?
Well, actually there is no difference. This is 45, right? 45 in the list is E. That's why it's writing E here. So this is 52. 52 in the list is R. Capital R, by the way. So it goes and writes R.
Okay.
It goes on like this. So there must be an O round here. What is O? Let me say. It's the 4F. Is there a 4F somewhere here? There must be a 4F somewhere here. Yeah, it's this. So that 4F is, if we count, let's do 1, 2, 3, 4, 5, 6, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's the character, 21st character from left. So if you just count that, O should be the 21st character from left. That's how it is.
Okay. Thank you.
Okay. Okay. So we can create arrays. We can create 8-bit arrays. And those 8-bit arrays actually can represent things like ASCII characters, and they're called strings. Actually, an array of characters is called string. You have used these words in C. When you created strings, there are character arrays. Remember character arrays in C? Character arrays is, it's like char. This was a type of a character array, right? When you created this, you were creating a sentence. If you remember from your C course, which is 154, right? No, 54. Okay, we continue. So that's strings. Strings are simply character arrays. So you know how to create an array. If you create 8-bit arrays, which have encoded characters in them, they become character arrays and they are called strings. In general, a string is generally considered a data type and is often implemented as an array data structure of bytes that stores a sequence of elements, okay? Typically characters, but not always ASCII characters, because if you want to write a string in Chinese language, since Chinese language has thousands of characters, you cannot use the ASCII table. There is a kanji table for that. And since that kanji table has to be thousands of characters long, it is not 8 bits, it is 16 bits, or I don't know how many bits, I don't know Chinese. They use another table. And if you create characters of that precision, imagine the kanji table, ASCII correspondent kanji table, I don't know, but is 16 bits, let's say that, because 2 to the 16 will be enough for representing thousands of images. Well, because 2 to the 16 is something like 6,000 something, 60,000. So it's like 65,000 kind of something. So each character will be representing a kanji, and there is a string as well. What I'm trying to say is strings are character arrays, yes, but they are not necessarily ASCII character arrays. They could be some other character table arrays. So if you have a fixed precision character array, those characters being encoded some generic table, ASCII, kanji, whatever, Japanese, whatever, then that's called a string. Okay? Good. Guys, I'm going to do some stuff on the thing that we have done on Kale as well before we finish. Well, this as the last slide, I have the midterm syllabus, which means these are the subjects that I'll be asking on the midterm, because in the previous week, we had the midterm on week 8. However, this year, we have the midterm on week 11, as you all know, sometime in December 18, as far as I remember. Correct me if I'm wrong. So guys, actually the syllabus is the same. Next week, we are going to start general purpose input-output GPIO. We're not going to include GPIO on the exams. These will be included, okay? Arrays, yes. Arrays, memory watch, register watch, and strings, characters. That maybe I didn't write it, but I should write character watch. Characters, ASCII, strings. I mean, I thought that they will be included because these are actually some titles and anything before them. So the midterm will be up to what we have seen up to now, today now. So the stuff that we are going to start on Friday will be in the context of the final. Okay? Any questions? So this is anything, midterm slump, anything in weeks 1 to 5 included.
Hocam,
Okay.
Memory kısmıyla nasıl bir soru gelebilir? Yani
Eski sınav sorularını ben paylaşacağım ya. Göreceksiniz memory ile ilgili nasıl soru geleceğini. Tamam. Çözeceğim de gençler bu arada, merak etmeyin. Tamam,
bir de bir şey soracağım. Az önce week 1 to 5 dediniz ama 1 to 7 yazdınız.
Sorry, then it should be 1 to 7. Thank you for the correction, guys. Let me write it then. Midterm syllabus is weeks.
Kafam karıştı. Hangisi olacak diye.
1 to 7. 1 to 7 included, which means 7 is also included. Clear now? Sorry, guys. Sorry. Clear. So everything up to now, today included, backwards. Okay, wonderful. Okay, so let's do this funny, simple, stupid stuff that we've done on Kale, and let's see how to do it hands-on. So when you try it on, you'll be able to do it more easily. So that would be easy for us. So let me just, so I've prepared simple code. This is some of the codes that I had from previous year's labs. So I create global variable here, and its name is A1. So your global variables can have any names. I mean, that was M in the example, but it's A1 here. It's just like the array 1, okay? And I'm going to write a simple code here. So I'm going to change these codes. I'm going to write some simple codes. So let me write. So let me just get my pointer first to R2. I like R2. So I'll have my pointer here. And I'm going to write the values to a memory location, which is, so first I'm going to be loading my values to memory. And I'm going to be writing those values to here. I don't need these. I'm going to delete these. So any questions about these three lines of code? I guess not.
Hocam bir şey sorabilir miyim?
Please.
Ya eski yazdığım kodlarda mesela str'ın sonuna B harfi ya da S harfine gerek olmadığını yazmışım. Çünkü direkt memory okuduğunu yazmışım da str'ın. Peki
str
burada
not reads the memory, it writes to the memory.
Right. Ha, tamam hocam.
That's LDR.
Peki o zaman hocam yine burada B'ye gerek var mı? Sonuçta hafızadaki bir yere yazmıyor muyuz?
Okay, good question. Let's try with strb, let's try with strh, and let's try with str. So see what is the difference. Let's do that example if you will. Okay?
Okay.
I think that's a good idea. I mean, since the question came, that's something we must do now. Okay, I save it, I rebuild it, I load it to my card, I start debugging, I say, okay, I haven't registered to Kale, and I press F5, now I'm waiting here. So guys, I press F10, one step ahead, the value of A1 is at R2, and it allocated this part, as you can see. This part, because it's, yeah, sorry, guys, I made a mistake. Because it put it in the code memory. I don't want this. Because code memory cannot be written during the code. So the directives were wrong. They are not responsible for this, but that's my mistake. So what I have to do now is I'm going to write them to here. So this will be code memory. And this will be, sorry for the mistake. I mean, this is not something you should know, but how did I realize this? Because I know which part of the memory is for code and which part is for data. And when I seen the value of that memory A1, which is assigned to, I quickly realized that it's a part of the, not the data memory, but the instruction memory, which shouldn't have been that way because I'm not allowed to touch the instruction memory during the code runtime. That's why I've changed it. Guys, these concepts are beyond assembly language and microprocessors. They are a part of embedded systems, the next semester's course. But since I did a mistake like this, I wanted to explain it to you because if you're interested, you can follow and this will help you understand it better. So I change it, I correct my codes. So not read-only, guys. This is not read-only. Sorry, guys, I'm going to just pause my share for a moment. I'm going to check something. Couldn't find it. And that's read right. Okay. Okay. Okay, so I resume share. So I'll put read write here. So instead of read write, because the data memory is a part of the memory where I can read and write during runtime. The instruction memory is a part of the memory I can only read, which I cannot write, read-only part. Which means, hey, compiler, select that part properly, I'm saying. Because if I choose the read-only part, I won't be able to change it during runtime. So certain parts of the memory has certain different physical properties. That's how we understand that. I'm asking the compiler to make necessary arrangements when I start my code. Hopefully this was going to be, oh my God, niye olmuyor ya? Bir build edelim, bir rebuild edelim. Allah Allah, bu niye olmuyor yani? Murphy yaşıyoruz da. Okay, so sorry, resume share. Okay, guys, I've created the memory part here. So I've created this global variable, which is A1, as you can see. And I'm going to use that A1. So let's do it. I just load this one, load it. So what is it? Is there what is the problem? This is not an opcode abicim ya. İyice saçmalamaya başladı. Ha, evet, o indentation önemliymiş. Okay, it's okay. I shouldn't have used the indentation. Sorry. Direktiflerde ben de şaşırıyorum. Okay, now the code is ready. As you can see, there are no errors. Okay, so I know that A1 is a global variable. Somewhere in the data memory will be allocated at A1. So A1, what is that place? I put it, it's 20 million. Now a part of the data memory I recognize. So it's going, let's watch 20 million. 20 million. So I'll be writing this value to R0 first. Let me do it. In R0, I'm sorry, I've written decimal numbers. Kimse de beni uyarmıyor. This should be hexadecimals, guys, because in the ASCII table, it is not decimal 45. Let me open the table. As you can see, I was going to write E of Erdem. It is 45 in hexadecimal. In decimal is 69. So let's write 69 for a good practice. Let's stop this. Let's write 69. So I start my code again, load it. Sorry, I start it again. F5'e basmışım da F10'a basacakken. I restart the code. Okay, so in R2 I have 20 million. I'm watching 20 million. In R0 I have 45. As you can see, I've used a decimal notation, not like a hexadecimal notation like this decimal notation, but R0 is always represented in hexadecimals here. It's 45. So STRB, which means it's going to transfer only one byte, the least significant byte, which is the 45, right? So it will be written to where are 2 points, here. So it will be 45. It was already 45 because of the previous program. So let's write another line of code. I'm going to make them strh, don't worry. So let's say it's R, which is in hexadecimals 52. So as you can see, I can put my immediate constants in decimals or hexadecimals. That's how I decide. So guys, let me write it. Okay. As you can see. So it's 45 in R0. Write that number to here, 45. Now 52 in R0, it's going to write it over here, not here, because I'm pointing to the same place. So it is becoming 52. If I wanted to write it to the next place, I should have put an offset, because that means do not write it directly to where are 2 points, write it beneath it. So regarding your friend's question, I'm not going to write the entire name. This is how you do it. Go home, try to write your own name. Okay. So what happens if you do H and STR H? Let's say STR, both of them. Let's try both of them. I rebuild it. Go. So I've got
Hocam çok kısa bir şey sorabilir miyim? Offset 1 dediğimizde tam olarak ne oluyordu?
Okay, let's get there. Okay, let's get there. I'll explain it when that line of code arrives, okay? So guys, it is here. So I'm here. I have 45. This is STRH now. It is going to read 16 bits from the register, write 16 bits to the memory. STR is again from the registers to the memory, but STRH is 16 bits. It's going to write 2 bytes, the least significant 2 bytes, which is the 00 and 45 hexadecimal. little endian tells me that the least significant byte will be written to the least significant address. So it's going to be writing it to where R2 points. R2 is 20 million. It's pointing to here. So it's going to write it here and here. This is the low address. This is the higher address. The least significant bit will be written to here, 45. The next one, 00, will be written to here. So if I make F10, 45, 00. So that's the difference between STRB and STRH. STRH have written 2 bytes. STRB was writing only 1 byte. Now, I get this value, 52. I have 52 in R0. I'm going to run this code. Your friend asks 2 things. What is STR difference from STRH? And what does this offset 1 means? We've explained it in the previous week. Go watch that video, but I'm not going to explain it again. This is STR, guys. It simply means get the value inside R0, write it to some memory location. STR, store it in the memory. Where in the memory? Where are 2 points? Plus this value, number of cells. Where are 2 points? It starts R2 points here because it's 20 million. And since I have written 20 million here, this is 20 million. But I'm not going to start from 20 million. 20 million plus the offset. 20 million plus 1. I'll start writing from here. How many bytes shall I write? This is STR. 4 bytes. I will write 4 bytes. I will start writing from here. So 1, 2, 3, 4. These 4 bytes will be written. What I will write, I'm going to write the complete 4 bytes in R0 to here, obeying little endian. The least significant byte being written to the lowest address, the others all read zeros, written to here, already zeros, because we have run this code. So if you do that, here and here. So that's simply it. So guys, and by the way, how to just show you, I've clicked, right-clicked. I had this, I've put ASCII, and the first 2 letters are already written. And I can just always get back when I see unsigned characters, okay? Go home, write your own name, right-click, put ASCII, and see your own name. Okay, that would be a good practice. Any questions? Arkadaşlar, ders videolarını yapabildiğiniz kadar tekrar etmenizi tavsiye ederim. Yani çok şanslısınız çünkü ilk defa bütün